Am I audible? Can you listen to me? Yes, I think I'm audible. So let's start today's session. Today we are going to discuss about transformation in 3D. Now, when we say three dimensions, things become more realistic as we actually live in 3D world. And now, mathematically and algorithmically, things are going to be a little bit complicated because you have an extra dimension here. So, how this session will go? It will be like the previous two sessions. First, you will go through the tutorial, and at beginning, I will like to say one thing: keep a notebook and pen with you, take notes, and after the tutorial you have to attend the quiz, and the quiz questions are from the tutorial itself. So if you carefully observe the tutorial, then quiz questions are not going to be much tough, and at the same time by attending the quiz you will be able to have an insight of the topic. So let me don't waste our time and start our discussion. In this tutorial, we are going to learn about transformation in three dimensions. Now, three-dimensional transformations take place in a three-dimensional plane. Now, as you know, how we define a three-dimensional plane, it's an object in three-dimensional plane can be defined in terms of three coordinate values x, y, and z coordinates. Now, for transformation in 3D, in this tutorial, we are going to learn about transformation in three dimensions. Now, three-dimensional transformations take place in a three-dimensional plane. Now, as you know, how we define a three-dimensional plane, it's an object in three-dimensional plane can be defined in terms of three coordinate values x, y, and z coordinates. Now, for transformation in 3D, you will need to have a deeper look into the three-dimensional perspective itself. Before that, just have a look at other properties. 3D transformations are important. Now, why they're important, you see, although two-dimensional transformations and two-dimensional representations usually seem simple to us, but our nature itself is three-dimensional. We ourselves view the things around us in three-dimensional space. You can see that onto your computer screen, whenever you see something other than what usually follows is that let me see picture of a mountain. So you can see that this is indeed a picture of a mountain. Now, my computer screen coordinate system is two-dimensional. But when you look at the picture of the mountain, then it gives you a sense of three dimensions because we ourselves live in three-dimensional space. So it is critically important to understand the three-dimensional coordinate system, three-dimensional representation of the objects. However, as there is one extra coordinate involved, things are going to be a bit more complex than 2D transformations. Now, this is just a reiteration of the previously known facts. Transformations are helpful in changing the position, size, orientation, shape, etc. of the object. Transformations will be same as you have studied during the two dimensions. Uh, you will have translation, you will have rotation, scaling, reflection, and shear transformation, as well as you will have the composite transformations and transformation with respect to some arbitrary location. Before diving deeper into the mathematical facets of different transformations, let at first we try to realize the 3D space itself. Now, 3D space in Cartesian coordinate system, you can see that can be represented using three primary axes. Here is your x-axis, here is your y-axis, here is your z-axis. And now the question goes here like, can a 3D Cartesian space be defined in terms of planes? If you look into simple two-dimensional coordinate system, two primary axes actually make your xy plane. This entire plane can be defined in terms of x-axis and y-axis mathematically. These x-axis and y-axis are nothing but two virtual lines which help us representing our two-dimensional space mathematically. Similarly, when you translate everything into three dimensions, there you will have a third axis called z-axis. Now you can visualize the three-dimensional coordinate system here, although this is drawn on the two-dimensional page. It gives you a sense of three-dimensional space because of the orientation of the lines. Now, can you think of this three-dimensional space in terms of planes? Just give it some thought and try to figure out. You can look that we were been able to define our screen, this white screen, in terms of x and y axis. That means by using two primary axes, we can define a plane surface. Now you have three primary axes. Now arbitrarily pick up any two primary axes, then you will get a simple plane. For example, let me discuss more about this. If you take into consideration x-axis and y-axis, then you have the xy plane, this vertical plane represented by blue rectangle. You can see that this blue rectangular plane can be assumed by employing x-axis and y-axis, horizontal x-axis and vertical y-axis. Now have a look at the uh, say this brown rectangle. This brown rectangle is defined in terms of x-axis and z-axis. Now this is the horizontal plane or floor onto which you are standing. Now just try to figure out the direction of the z-axis. It feels like as if someone is looking towards this three-dimensional space from this direction, that means along the z-axis. Now come back to our previous discussion. I must digress. If you look into this green rectangle, this green rectangle can be defined in terms of y-axis, vertical y-axis and z-axis, which is pointing towards the viewer. Now try to find out another property of these three planes which can be defined in terms of your primary axis. These planes are basically perpendicular to one another. If you observe carefully, you can figure it out. This xy plane, that means blue plane, you can see that is perpendicular to the brown zx plane, and this green zy plane is again perpendicular to the horizontal xz plane. I hope this makes sense to you. So a three-dimensional space you can represent by using three perpendicular primary axis or three perpendicular primary planes in other way. So this was the idea behind this diagram. Now let me explore some more properties of three-dimensional space. Now here you have three different types of representation for three-dimensional space. You can represent it by orthogonal axis, xyz axis, using Cartesian coordinate system. You know that a three-dimensional space can be represented as if everything is inside a cylinder, as it is being done in cylindrical coordinate system. Then you can represent it using spherical coordinate system. Under this spherical coordinate system, the assumption is that as if you are sitting inside a sphere, and with respect to the center of the sphere, you are looking at different directions. So this was about different coordinate system representations of the three-dimensional space. If you want to know more about the other representations which we are not going to use in computer graphics, say cylindrical coordinate system or spherical coordinate system, you can surely dig internet and find more about them. Next, have a look into this diagram. Locating a point in 3D space. A point in three-dimensional space can be represented using three tuples or three coordinates: x coordinate, y coordinate and z coordinate. Now mathematical significance of this coordinate is something like this. Say you have a arbitrary point P into the 3D space or your x, y, z space, and its coordinate goes like 4, 5, 5. That means x value of the point is 4, y value for the point P is 5, and z value for the point is 5, and the geometric significance goes like the distance of the point from the x coordinate is 4. That means this distance is 4. Then the distance from the y-axis here to the point is 5. So this distance is 5. Now you have to go to the vertical direction, and the distance from the point to the z-axis is 5 again. That means this distance is 5. So from the origin 0, 0, 0 to arrive at point P, you have to travel 4 points along the x-axis. 1, 2, 3, 4. Then you have to move 5 points along the y-axis. You can see 1, 2, 3, 4, 5. So along the y-axis you have moved, or you have displaced your cursor 5 points towards y direction. Then you have to move 5 points towards the vertical direction. Let me correlate. 1, 2, then 3, then 4, then 5, and we are done. We have arrived at point P. So this was how a point is represented in three-dimensional Cartesian space. Now let we move forward. So here is something which you must get hold of for a better understanding of transformation in 3 dimensions. View. When you talk about 3 dimensions, then view becomes an important thing. So this is the side view of a 3-dimensional object. So if xy plane represents your horizontal space, like this diagram, no, not like this diagram. In this diagram, xz was the horizontal space, and in this example, your horizontal space was defined in terms of xy plane, and yz plane represents the vertical plane. So if you get the side view of this 3D space, you will not be able to see the x-axis. So can you give it some thought? Think for a moment and try to figure out where is your x-axis, in particular this diagram. Yes, the x-axis is basically here. As you are looking to the x-axis, looking to the yz plane along the x-axis, or more precisely standing on the x-axis itself, the x-axis seems like a point to you, and this is the top view of the object, where you are looking at the object from this point. Sorry, here is your eye, and along the z-axis you are looking into this direction. So you can see that Z-axis is basically uh, now a point, or it seems like a point here. So to get more understanding of this thing or this perspective view, let me look into a software called Blender. I'm not endorsing it, and the mandatory disclaimer is that I'm not an expert of this software. This is basically an animation making software, 3D animation making software, and I found something interesting which we can use to understand this 3D perspective more clearly. Uh, at first, have a look into the orientation of the primary axis system. This red line is your x-axis, this green line is your y-axis, and this blue line is your z-axis. Now, if you this was the mathematical representation for the axis system. Now, if you come into the main object space, you can only see the x-axis, this red line, and y-axis, and a 3D object or 3D cube into this XYZ Cartesian plane. Now, can you imagine the direction of the z-axis? Yes, it is basically must be in this direction. Sorry, yes, in this direction. You can match it with the original orientation of the z-axis. So let we erase this dirty z-axis and play with the 3D space for some time. Now, camera, yes. The assumption is that you are looking to this 3D object from somewhere here. You can see the camera here. So the assumption is that you are looking into the object from from this point of view into 3D space. Now, for the time being, let us assume that you are standing here. This is your eye, and you are looking into this direction. Now, how everything will be seen by the eye? Let me try to manipulate everything. Yes. So let me align it for you. Yes. You can see that x-axis now seems like a point of, or more like the origin of the 2D space defined by y and z-axis system, and the 3D object which is not where, it is still a 3D object into the xyz plane. But as you are standing onto this x-axis and along the straight axis, in this direction you are looking into the object, you are only getting the side view of the object, and it seems like a square to you, right? Now, let us try to get the top view. So to get the top view, just imagine, think for a second, give it some thought. Top view means you want to look into the object from top, from this direction. So that means you want to look it onto the xy plane from z direction. So how everything will go like, Just give everything a rotation. Yes, this is the top view. You can see the x-axis and y-axis, and it seems like our well-known two-dimensional coordinate system. This is the top view. Now I think uh, where is my cursor? Yes. Uh, Now I think this top view and side view thing make sense to you. You are going to use these concepts while you will study about rotation in 3D. For today, we are going to study only the translation thing, the simplest one. So, can you think of translation into 3D? Yes, you can do it something like you have a point x old, y old, and z old in the 3D space or 3D Cartesian coordinate system defined by x-axis, y-axis, and z-axis. Now you want to apply a translation Tx along x-axis, Ty along y-axis, and Tz along z-axis onto your original point x old, y old, and z old. After applying translation, you arrive at some other location, which in our diagram is x new, y new, and z new location. Point O is your original location, and after applying the translation, O dash is your new location. If you can recall the transformation in 2D, the formulations will be same. Now x new will be x old plus tx, y new equals to y old plus ty, and z new equals to z old plus tz. Now, as we have studied during the transformation in 2D module, you have to convert everything into homogeneous system. For the ease of use, let me introduce the homogeneous one. As there are 4 equations now, you can surely say that your transformation matrix will be a 4 by 4 array. So let me convert these 4 equations to a single equation involving matrix xn, yn, zn, 1 onto the left hand side, and onto the right hand side you will have 1 0 0 dx, then 0 1 0, this is 0, yes, ty 0 0 1 tz at the next row, and at the last row you have to adjust it for the homogeneous coordinate. So here we go, and multiply this with your original point, which was defined by x old, y old, z old. We are done. You can see that if you do the multiplication on the right hand side, you will arrive at the same conclusion as these four equations. 1 multiplied with x0 plus y0 multiplied with 0 plus z0 multiplied with 0 plus tx multiplied with 1. That will be equal to x new, and so on. So here is your translation matrix in 3D. It was simple, unlike the 2D transformation. Translation matrix in 3D. Let me erase this dirty arrow and put the dirty arrow here. So derivation was simple. Let me scroll it up. Yes. Here's the statement. Just have a final look. Consider a point object O has to be moved from one position to another in a 3D plane. Initial coordinates of the object O was x old, y old, z old, as we have discussed. New coordinates of the object O after translation goes like x new, y new, z. Oh, here I have a mistake. It should be z new. Then translation vector or shift vector is tx, ty, and tz. Now this translation vector signifies that tx is the distance the x old coordinate has to be moved into the x direction. Ty defines the distance the y old coordinate has to be moved into the y direction, and tz defines the distance the z old coordinate has to be moved into the z direction. So after the movements defined by this tx, ty, and tz, you will get something like this: x new, y new, z new, and their equivalent right hand sides. Now to convert it into homogeneous matrix representation, you have to introduce the homogeneous 1 equals to 1 at the end of the three equations, and you will get this matrix representation here. So this was all about 3D space and translation in 3D. Now is the time for the quiz. Just a moment. Yes, fine. So here is the quiz. You can find it into the Google Classroom. It is not live yet. I'm going to make it live now. There are 10 questions into the quiz. All the questions are mandatory. It's 12:08. I think 15 minutes will be enough to complete the quiz. So it's 12:08 and 12:18. So we are going to end the quiz session at 12:23. 12:23. I think 15 minutes will be enough to complete the quiz. So I'm going to share the quiz hyperlink in the chat box also. But you can find it into the Google Classroom and you can start it. So start. I think I should also share the form link with you. From the second hyperlink, you can directly access the quiz. You don't have to go to Google Classroom. I think I should also Yes, the day is not bad. Until now, we have one, two, three, four, five, six. Six guys who have scored 20 out of 20. Moshihiro, Satik, Rahul, yes. ABC at gmail.com. Not being able to get who is this. I can see that someone named Movie Fan has also scored 20 out of 20. Now, Movie Fan seems a peculiar name. I have never heard of such name. Can you please write down your original name into the chat box? I can see that someone named Movie Fan. At least try to use your original name in this kind of things so that everyone watching you can know who is the guy. Now I can see that Ratno, Ratnopia is not having a very good day today. Only 6 out of 20. This kind of things. So that I hope that most of you are done with the quiz already. Is there anyone who is not done yet? So today it is not the girls' day. All the girls have scored very poor. So today it is not the girls' day. All the girls have scored. So we are almost near the end of the quiz session. Just 1 minute left. Let's see. Now, by watching, you see this bar graph and looking at the scores of your fellow participants, you can compare yourself with others, where you're standing. So, this is actually the concept of percentile. From this type of concept, the concept of percentile actually emerged. So, it's 12:23. We can end the quiz session now and let's start our discussion. So the first question is homogeneous coordinates are not applicable in 3D transformation if the statement is true or false. Now look at the slides. Homogeneous coordinates are indeed applicable in uh, 3D transformation, and at the end you have to represent and implement all your algorithms using homogeneous coordinate system. So the answer here is true. Let me move to the next question. Suppose you have a point 444. What will be the resulting point if you apply a translation by -1, -1, and -1? So goes like into the 3D space. Let me try to draw it another way. X, Y, and Z. You have a point 4, 4, and 4. You have to apply a translation by an amount of -1, -1, and -1. So you can do it in two ways. Let me do it mathematically. X dash, y dash, z dash 1 equals to. Now you have to place the translation matrix 1 0 0, then tx. Tx is -1, this -1. Then you have to assign the next row 0 1 0 minus ty, and ty is -1 for this problem. Then you have to place the row for z 0 0 1, then tz, and tz is again -1. This is tz, and tz is -1. And last row for the homogeneous coordinate, then you have to multiply this matrix with the original input point, that is 4 4 4, and lastly you have to append the homogeneous one. If you do this multiplication for x dash, you are going to get 1 multiplied with 4 minus -1 into 1, that is 3. Similarly, for y dash you will get 3, and z dash you will get 3. So the correct answer is the first option, that is 3 3 3. Now let me move to the next question. And the question goes like, if translation matrix is implemented as a two-dimensional array, then what will be the value at 0 3 location? So you can thought of the translation matrix as a two-dimensional array. So we can assign array location to them 0 1 2 3. That means we have subscripted the rows. Next we will subscript the columns 0 1 2 3. Now the question is asking for the value at 0 3 location, and at 0 3 location you have tx. So the answer is tx. Next question. Translation is a linear transformation. True or false? If you look at the equation for translations, all the equations are basically linear equations, because the highest power in these equations are 1. So from this, the fact which follows is the statement is true. Yes, some of you have already started writing down your roll number into the chat box. Those of you who have not done yet, do it, as we are close to the end of the session. Next question. In front view or top view, one of the primary axes might seem like a point. Now for this, you have to go back to this Blender example. Here you have the front view of the object. Now one of the primary axes, that is x-axis in this case, you can see in the axis system that it more looks like a point rather than a line. So yes, uh, it might seem like a point. So the answer is true. Can 3D space be thought of as a sphere? Well, we have already discussed it. There are different coordinate systems which you can use to represent a 3D space, and one of them were spherical coordinate system. You can see it here. So yes, a 3D space can be thought of as a sphere. The answer is yes. Can 3D Cartesian space be defined as a collection of perpendicular planes? If you can remember this example, you can find that a 3D space or Cartesian 3D space can be represented as a collection of perpendicular planes. Here xy plane was represented in blue, yz plane has been represented in green rectangle, and the horizontal xz plane is represented in brown rectangle. Now you can see that these three rectangles are basically perpendicular to one another. That means the angle between the rectangles is 90 degrees. So the answer is obviously yes. Uh, in 3D Cartesian space, are all the primary axes orthogonal to each other? Orthogonal means the angle between the lines will have to be 90 degrees. So two lines x and y will be orthogonal to one another if the angle between the lines is 90 degrees. Now in 3D Cartesian system, the x, y and z axis, which are primary axes, you can see are perpendicular to one another. Lastly, x, y, y, z, and this is the angle between x and z. No, y and z, yes. So again, this is going to be true. They are indeed orthogonal to one another. Last two questions. Suppose a cube is centered as 0, 0, 0 and its sides are perpendicular or parallel to primary axis. The front view of the cube will seem like what if the viewer is looking toward the cube while standing on one of the horizontal axis? So let me again look at this example. Uh, you can see that this cube, the center of the cube, is located at the geometric origin of the 3D XYZ space. Now, the problem goes something like, say, you are, yes, looking at the front view for the object, that is the cube, by standing on one of the primary axes. That means you are standing somewhere here, and this is your eye, and you are looking along the x-axis towards the front view of the object. Now you can guess what the object look like. Uh, it actually looks like a square, if you can see. So yes, square is the correct answer. And the last question for today: if translation matrix is implemented as a 2D array, then what will be the value at 1 3 location? Now for this you have to remember the general construction of translation matrix. Now it is asking for the value at location 1 3. That means that we use another color. It is asking for this value ty. You can see that at 1 3 location the value is ty. So this is the correct answer. So I hope you have been able to grab the concept, and if some confusions are there, then go through the reading material, that means this thing, and watch the tutorial video carefully, take notes, then attempt the quiz once again until you get 20 out of 20. Once you get 20 out of 20, be honest to yourself. Don't copy the answers. Make sure that you have got a sound realization of the questions and logic behind the answers. Once you get 20 out of 20, you can say that you have been able to get an understanding of the concept. That was all for today. So enjoy the rest of the day. I am disconnecting myself now.